All right, let's talk about something that's hiding in plain sight. It's this hidden engine that's powering pretty much everything we do in our digital lives. But, most of us have probably never even heard of it.
So let me ask you something. What is the one piece of tech that forms the foundation for, well, everything? For the giant cloud data centers, the super fast 5G networks, the very fabric of the internet you're using right now? The answer? Well, it's probably not what you think. It's not some big company or a shiny product you can go out and buy.
No, it's an invisible engine. It's humming along, constantly working, constantly evolving, right underneath almost every single service you touch.
And that engine is the modern Linux kernel. So today, we're going to pop the hood and really understand the incredible, revolutionary new features that are making our entire digital world tick. So first, let's peel back the layers here. For a long time, the Linux kernel was, powerful, but it was also kind of rigid. But recently, a whole series of absolutely radical new capabilities have turned it into something way more dynamic, way more powerful. Okay, so now for the really cool part. Let's get into what I'm calling the kernel's new superpowers. These are the game-changing features that engineers are using right now to build the technology of tomorrow. First on the list is this thing called eBPF. Now this is wild. The best way to think about it is, imagine you could safely install these tiny, programmable micro-robots directly into the nervous system of your operating system. That's basically eBPF. It lets developers run these little custom programs right inside the kernel itself, without ever touching the kernel's core code. I mean, that is a huge, huge shift. So what can these little micro-robots actually do? Oh man, the list is staggering. They can steer network traffic at insane speeds. They can watch for security threats as they happen in real time. They give you this unbelievable visibility into what a system is doing, and they can even filter out massive denial of service attacks before they even get close to your apps. So here's the absolute game changer. You get the raw, pure speed of running code right at the kernel level, but you also get the safety and the flexibility of not having to recompile or risk crashing the whole system. That's exactly why massive companies like Cloudflare and Facebook, who operate at a ridiculous scale, are all in on eBPF to run their infrastructure.
Okay, next superpower, I/O Uring. This totally changed the game for how programs handle data. So look at the left side here. That's the old, slow way. Every single time a program needed to read or write data, it had to ask the kernel for permission, which created all this slow back-and-forth chatter. But now look at the right. That's I/O Uring. It basically sets up a high-speed express lane between the app and the kernel, almost getting rid of all those requests. And the result? A giant leap in performance and super, super low latency. This is a total game changer for things like high-performance databases and web servers.
All right, let's shift gears and talk about the tech that makes things like Docker and Kubernetes work. The very first ingredient is something called namespaces. And the easiest way to think of a namespace is as a virtual bubble. When you stick an application's processes inside this bubble, it can only see what's in its own bubble. It's totally, completely isolated from everything else running on that machine.
But just putting things in a bubble isn't quite enough, right? What happens if one app in its bubble decides to go crazy and eat up all the computer's memory? Well, that's where the second key ingredient comes in, control groups, or C groups. Think of these as resource budgets. They set these hard limits on how much CPU time or memory or network bandwidth any one of those bubbles is allowed to use. It stops one bad app from taking down the whole server.
And right there, when you put those two kernel features together, the isolation bubbles from namespaces and the resource budgets from C groups, you get the foundation for all modern container technology. That's the magic. That's what's behind Docker, and it's what's behind the entire Kubernetes ecosystem that pretty much runs the modern cloud.
Okay, so we've been talking about some pretty powerful but kind of abstract features. So let's connect them to the real-world stuff that we all use every single day, because this is where it really gets fascinating.
So who's actually using this stuff? Pretty much every major industry on the planet. Your cloud providers? They're relying on the kernel's virtualization to run everything. The big telecoms? They use its real-time capabilities to actually power the 5G networks connecting our phones. And super high security places, like financial systems, they absolutely depend on the kernel's advanced security to keep critical data safe.
And this table just lays it out so perfectly. You can literally draw a straight line from a single feature deep inside the kernel to a piece of global technology. Improvements to KVM, which lets one computer act like many, well, that directly enables the public cloud. Preempt RT, a feature for ultra-precise timing, is what makes 5G and advanced robotics possible. And these modern file systems? They're the bedrock for gigantic data centers. It's a direct line from code to reality.
So when you kind of zoom back out and look at all this, you start to realize something. Understanding these kernel features isn't just for hardcore engineers. It actually gives you a brand new way of looking at all of technology.
It's really not about memorizing a list of features. It's about building a unified mental model. You stop seeing technology as all these separate, disconnected boxes, and you start seeing how it all fits together as one single, coherent system.
And how do you build that view? Well, you start connecting the dots. You start to see how the design of a CPU directly impacts how the kernel schedules tasks. You get the link between how memory is managed and how files are stored on a disk. You see exactly how the kernel's networking code is the foundation that lets containers talk to each other. And then, all of a sudden, it just clicks.
And let me tell you, this kind of knowledge is incredibly valuable because it is future-proof. The next big waves in tech, whether we're talking about AI, edge computing, the next phase of the cloud, all of it is being built on top of the Linux kernel. If you understand the foundation, you have a massive advantage in understanding where everything is headed.
So that leaves us with one last, really fascinating question. After seeing the incredible leap in what this thing can do, if this is what the modern kernel lets us build today, what new, maybe even unimaginable technologies will it be the engine for tomorrow?